Alrighty. So at the end of Friday's class, we finished off looking through, well, effectively what we did is we looked through three different examples where each example was meant to illustrate why developing, let's say, like proper sampling techniques would be a beneficial practice. The three examples were a very different structure. So, for example, in the first case, what we were illustrating was a situation where we have a non-representative sample. So that was the example that focused on the questionnaire that was sent out well, it turned out that this questionnaire was sent out to female or women's groups, and it was asking them basically for feedback on their relationships. And in the end of it, the author cited, well, I cited four different statistics that came out of that particular questionnaire. But the issue was that these statistics were being generalized to the entire population when the sample was not representative of the entire population. So this is one situation that, of course, we would like to avoid, because based off of our very early discussions, we know that having a representative sample is one of the most important goals of our sampling strategies. In the second illustration, what we saw an example of was a situation where a very short survey was sent out to what we can assume was a representative group of American people, but the question on the survey was very complicated, or confusing is probably a better word. So the response to the question was alarming because it indicated a certain disbelief in what is a documented historical event. And then the third illustration is an example of a more modern problem. And in many cases, what this illustrates is an issue with non-response and an issue with unreliable, well, let's say there's issues with non-response and issues with the responses that you are getting being unreliable. So the third example focused on the 2016 presidential election, where early polls indicated that the Democratic Party was ahead of the Republican in terms of electoral and popular vote. But of course, in the end, the Republican Party won that election. And a few different things came out of this. For example, there was a discussion on how pollsters are efficient or somewhat efficient in predicting the popular vote, but the correlation between the popular vote and the electoral vote isn't necessarily as strong as it needs to be in order for, or needed to be, I guess, in order for these results to have been true. There was also an issue with non-response, as I said before, because such a large percentage of the population has cell phones now, so it's harder to actually get in contact with people. Finally, the issue with non-response, as I mentioned before, had to do with, I think, something that was fairly well documented, this idea that people were somewhat scared to say they would be voting Republican in this particular election. So they either lied when they were contacted, or they, again, didn't answer their phone. So in the end, the actual result in terms of the electoral vote did not mirror, or was the opposite of what was predicted. And there's all these different reasons as to why that could have been the case. All right, so from our point of view, so from the Stat 350 point of view, what we are trying to get at now, or what we are using these examples to do, is motivate our study of proper survey sampling techniques, or maybe instead of saying proper, of survey sampling techniques in general, and to try and illustrate why these would be beneficial to us as we progress, or as we go out to collect data, so that we can make inferences about a population. And again, one of the things that these examples illustrate is that there are a lot of things that can go wrong, and that there are a lot of considerations that have to be made when we are putting our surveys together. And we'll talk about some of these ideas later when we talk about questionnaire design, albeit this will be a fairly brief discussion, but these ideas will be wrapped into that particular discussion. Okay, so we have established that there is a need for sampling protocols that can lead to representative samples, especially in the situation where we want to make reliable inferences about some target population of interest. We need to be able to collect information from that target population to create what we would consider to be a representative sample. And again, when I say representative sample, essentially what I mean is a sample that in the perfect situation would be a scaled down version of the population. And that is to say a sample that inherits or embodies the characteristics of the target population, which of course are going to be multifaceted. All right. So as we mentioned earlier on, an ideal sample is going to be one that is a scaled down version of a population. So in a very simplistic situation, let's suppose that we have two characteristics or two variables or two features, gender and employment status. Okay. Okay. So you can see in the first contingency table, the one labeled population, we have 10,000 males that are employed, 10,000 females, or 8,000 females that are employed, 500 males that are unemployed, and 300 females that are unemployed. The sample in this case would be what we would consider to be the scaled down version of the population, where effectively we've just divided everything by 100, but we're capturing these features in the same proportions as they exist in the population. Okay, so this would be a very simplistic illustration of this mirrored version. All right, now when we go to actually select the sample, we can start by differentiating between two major types of sampling strategies. On one side, we have what we would consider the probability sampling scheme. This would be the sampling schemes that we're going to be most interested in this course, so the ones that we will study most often. And then on the other side, we would have what we would consider to be the non-probability sampling schemes. So really what we're differentiating between is an element of randomness in how we select observations for our sample. We will come back to define many of the labels and terms and symbols that we're going to use in our probability sampling scheme a bit later. But for now, we can just mention that capital U is the symbol we use to designate the sampling frame. And the sampling frame ranges from 1 to capital N, which is the population size. But again, I will come back to define these once we actually start talking about probability sampling in the next lecture set. Okay. So as a simple illustration, again, what probability sampling really does is it just attaches a probability to each of the different observations within the sampling frame, such that each observation has some probability of actually being selected for the sample. Now, let's suppose for illustration that we have a sampling frame that has 1,220 different records in it. So we are assuming here that the population size is 1,220, and we're going to select 20 of these to be in our sample. We don't necessarily have to give every single observation the same probability of being selected, but if we did, then we would essentially be doing what is called simple random sampling, which is generally considered to be the simplest type of probability sampling scheme. And as I mentioned on Friday, this will be the sampling scheme that we actually spend the most time discussing. It is truly the sort of foundational scheme for all of the other approaches that we're going to study in the course. In fact, once we move on to approaches like stratified sampling or cluster sampling, what you will notice is they are really simple random sampling schemes where we are changing the sampling unit to accommodate for the design of the experiment. Okay, so again, we're going to talk about this in more detail later, but effectively, the idea here is that we're going to attach the same probability of being selected to each observation. And as a result, we can say that the probability of observing a sample of size 20 from this particular sample frame is going to be 1 over 1,220 choose 12. And we'll come back to define these probabilities later on as well, and talk about selection probability for each sample and each individual unit. But the idea here, again, is essentially that probability sampling attaches an element of randomness to each observation being included in the sample. And therefore, from a sampling frame with a fixed population size, we can then write out the probability of each of the different samples being selected. Non-sampling protocols, of course, would not have this element of randomness or this probability being attached to each of the different observations. Non-sampling protocols can be divided into different types. For example, on slide 28, I have 4 different non-sampling protocol schemes. Convenience sampling. This is essentially a take what you can get approach. I think the name itself is fairly self-explanatory. It's basically just saying, if you want to collect information, you just, take whatever is in front of you. So, if you're in a classroom, I would just sample the people that are in the chat today and use you as my sample because it's convenient. Self-selection sampling, the units choose themselves. So, for example, you're responding if you're interested in responding. So this would be the type of thing that you see on, Facebook or Twitter, for example, when polls are put up by your friends or by people that you're following and you choose to respond. Quota sampling, which is one we're going to talk about in a little more detail because this is an interesting idea, is the idea of selecting units such that you account for or fill the number of, well, let me put it this way. In the simple illustration that we looked at a few slides back, where we had the population with employment status and gender, and we had the ratios of each of those different characteristics to one another, quota sampling would be used to fill each of those values such that those proportions are intact. So, for example, if we look at that previous slide again, and we notice that in our sample here, we had 100 male employed, or for male employed, we had a count of 100. For female employed, we had a count of 80. For male unemployed, we had a count of 5. And then for female unemployed, we had a count of 3. We could say that these are the quotas. So these actual values are what we want to obtain such that we can go forth and perform our analysis. So quota sampling would basically set out to find 100 male employed persons, 80 female employed persons, 5 male unemployed persons, 3 female unemployed persons. So you could consider those to basically be the numbers that you need in order to satisfy the experiment. So the quotas, and then we seek to fill those. Now, as I mentioned, we're going to talk a little bit more about quota sampling in some detail, because I think a natural question that might fall out from this idea is, this seems like a good sampling scheme because you are essentially creating a scaled down version of the population by filling these quotas. So if a representative sample is in fact a scaled down version of a population, and quota sampling would fill the quotas for the different characteristic combinations, this would create a representative sample, right? So we'll talk about that versus the probability sampling scheme momentarily. The last example of a non-probability sampling scheme is judgment sampling. So here we have units are selected so that the samplers think that the sample will be representative of the target population. Right, so this, this idea kind of plays off the quota sampling idea by the description that are given, by the description that's given here. We're basically saying that based off of some expert opinion, we're going to fill the sample such that all the characteristics that we require for the sample to be a scaled down version of the population are intact. Now, I think that some of the issues that could go wrong with this are fairly self-explanatory, but these 4 examples illustrate what we would consider to be sampling schemes that do not have an element of randomness attached to them. So people are essentially pulled into the sample, um, there's an unequal probability. Let's say of people being pulled into the sample, you are chosen to fill a certain quota, or you're chosen because you are standing there and it's convenient, or you are chosen because we need someone with your characteristics to help us create the representative population. All right. So probability versus quota sampling. So as I mentioned before, the idea of quota sampling is an interesting idea because it would, by definition, create a representative population. If a perfect representation of the population is in fact just a scaled down version of the population, then quota sampling would be a very reliable technique to help us get there. So the question is, if we were to use this approach, would this not give us a sample that actually adheres to the features that we are looking for? So would this not provide us with a, a representative sample? So if we took the quota sampling approach, could we trust that the sample that we achieve, or the sample that we collect, is actually representative of the target population? So in short, the answer is most likely no. So then the question becomes, well, if quota sampling does in fact fill quotas where each quota represents a certain characteristic combination of interest to us, or a certain characteristic combination that represents what we observe in the population, then why wouldn't this be representative? The answer is essentially that in a very simple contained experiment where you have a population that for whatever reason only has two features, this sampling scheme likely will create something that's representative. However, very few populations in practice are actually composed of only two factors. So very few target populations without some sort of manipulation are only going to have, let's say, a small number of features that we have to consider. The other thing to keep in mind is if we were to view the characteristics of our population through the idea of a contingency table, every time you add another level to one of the features, or you add an additional feature, the structure of that table becomes more and more complicated. So in the situation where we have only two features, so gender and employment status, and each of those features has only two outcomes, we have a 2 by 2 table. But let's say that we add another level to one of the features. So let's say with employment status, you add another level, and with gender, you add another level. Now you have a 3 by 3 contingency table. Okay, so things are starting to get a little bit more complicated because now you have to consider more combinations of features. If you add another feature, you add another dimension to the contingency table. So now you could have sort of an array, if you want to think of it like that, or you could have a 3-dimensional table where you now have another axis coming out. So if that has two labels, then you now have 3 times 3 times 2 different combinations to consider. And every time you add a feature, you multiply the number of different combinations that have to be considered. So the population dynamic becomes complicated very, very quickly. So trying to find all of the different feature combinations and the appropriate quotas for those feature combinations would be very taxing and very difficult, and in some cases likely impossible. Probability sampling, on the other hand, would more naturally provide us with a way of, well, where's the, yeah. So probability sampling, on the other hand, should naturally provide a representative sample where the characteristics are fairly balanced because of the fact that we have this inclusion probability attached to each of the different persons. So the idea here is essentially if you give every single observation in the unit or in the sampling frame the same probability of being selected, then each time you collect a sample, the probability that that sample contains all of the probability, or sorry, uh, each time you collect a sample from the frame, because you have attached an element of randomness or equal inclusion probability for each unit, what you should get out is a sample that is naturally representative of the target population, because the features of the population should occur at the same rate in the sample. Now, that being said, of course, you're going to run into issues with this scheme in the same way that you will with the quota sampling scheme. The main difference, or one of the other arguments that you might make, though, in favor of the probability scheme is that you don't have to go through the process of trying to determine what all of the different features are and the rates at which all the different features occur, or the proportions at which all the different feature combinations occur. With the random sampling scheme, you can trust the process and just use it to collect information, and then have sort of in the back of your mind the idea that this should be representative because every unit was given the same chance to be included. The other thing, of course, that has to be considered is sample size is obviously going to play a role here. If you collect a very small sample from the frame, it's unlikely that you're going to get the balance or the representation that you're looking for. But the more information you collect, the more likely it is that you're going to see a representative sample. The other thing that's beneficial about randomization or probability in general is that it allows us to conduct inference in the ways that we are accustomed to. So by using a probability sampling scheme, what we're then doing is basically, what we can then do is make assumptions about the shape of the target population, so we can make distributional assumptions. We're now randomly sampling from a statistical distribution. And of course, by doing that, what we can then say is what we can then do is conduct inference in the familiar ways, i.e. via hypothesis testing and confidence interval construction. So we can attach statements like that, which would be attached to a confidence interval, and say that we are some percentage confident that the parameter of interest is in between the lower bound and the upper bound of that interval. So it gives us inferential capability, and it allows us to use the statistical techniques that we have established or in previous courses. Okay, so no sampling scheme is perfect. You're not necessarily always going to be able to trust the sample. We know from our previous studies, or even from the definition of a confidence interval, that there is some, that we're going to collect a sample that misses or doesn't contain the true mean once we build the confidence interval, or we're going to collect a bad sample that isn't representative or is taken from a certain part of the frame where we're maybe only using outliers and this kind of idea. But what probability sampling does do for us is it at least allows for us to use the conventional statistical techniques that we are accustomed to, so that we can conduct inference and we can make statements about the population of interest, and we can bound our estimates, and we can account for the sampling error that's going to naturally occur when you're only using a subset of the population anyways. So when you compare this particular non-probability sampling scheme to a simple probability sampling scheme like simple random sampling, in the end, the probability scheme is going to give us more statistical capability than the non-probability sampling scheme would. But again, neither situation is perfect. I don't want you to leave here today and say, well, this is bad and this is good. I mean, they both have their own merits. And depending on this type of population you're studying and what you're interested in, the quota sampling scheme could still be useful. But in a larger, more complex and dynamic population, the probability scheme is going to be one that we can use to build more meaningful statements, at least in my opinion. Okay. Does anyone have any questions before I start talking about some of the errors? I'll have to timestamp this on YouTube, rant about probability versus quota sampling. Okay, so we only have a few things left to discuss before we can actually start to get into some more of the mathematical details. Um, so we're going to talk about errors and we're going to talk about biases. Biases. In survey sampling, or in this course, there are effectively three major types of error that we need to be aware of. The first one is called the study error. So this is the difference between the attributes of interest in the target and study population. The second one is called the sample error, which is a difference between the study population and the sample. And then the third one is called the measurement error, which is a difference in due to, or the difference in attributes of interest due to the difference between the true and measured values of the variance on the units in the sample. Okay, and then we can also call study error frame error. So what is the basic idea here? The study error or the frame error can occur when the frame and the target population don't align. That's the idea. So if we have a study population or a target population, I'm sorry, that's, like let's say over here, and our frame starts in the middle and then has a large part that's outside of that target population, and we end up sampling from the part outside, that of course is going to create error. So the study error is an issue with how the frame and the target population align, essentially. The sample error is a similar idea, except now we've already collected from the frame. So if our frame is sort of, this portion over here, and then the population is partially aligned with the frame, let's say like half of the frame aligns with half of the population, and then there's two sections that are not connected, then in that case, we would have, when we collect our sample, if we end up sampling from the portion that's not inside of the target population, now we have a misalignment between our sample and our target population. And then measurement error, I think, is the most self-explanatory type of error. This is an issue with collection, and this can occur in a lot of ways. I mean, this measurement error can be attributed to many different things. I mean, someone lying and giving a misleading result. If there's an interviewer involved, them writing down the wrong answer could be measurement error. This is essentially just a disagreement between the true value in the population and the value that was sampled from the same unit. Okay. So these are the three major types of errors that we would have to be aware of, or we would be concerned about when we are using our sampling schemes. Okay, so going back to the idea I gave before, an example of study error is coverage. And again, coverage refers to the frame not matching up with the population. So this idea here, if we were to draw, say for example, a rectangular population. I always go with rectangles for the population. Maybe I should start switching. Every year I should switch the shape up just for kicks, right? And then let's say our frame, so we'll draw the frame in blue. Now let's say that our frame kind of sits like this. Oh, I want a perfect box. Like that. Okay, so here's our frame. So this would be the idea, at least in terms of coverage. The frame is not accounting for, or is not entirely included in the target population. We have a misalignment here. So there's a very good chance that we could collect information that's outside the target population. And then this can occur for different reasons. I mean, outdated email lists, outdated server lists, basically just anything that could lead to our sampling frame being outdated, for lack of a better term. Okay, an example of sample error. So this is a misalignment between the sampled population, or the sample and the target population, would be non-response, which is probably the most serious type of error. So this refers to the unit not giving, for example, a useful answer. But the idea of not giving a useful answer can be multifaceted. I mean, this could be them simply not replying at all, to replying but lying. I mean, anything sort of on that scale could be considered a non-response issue. Okay. So let's talk a little bit more about this idea of non-response. So in this illustration here, we're considering our sampling frame, right? And then inside of the sampling frame, we have our actual sample, which is this sort of elliptical like shape down here. And then we have actual sample pointing to this whole circle. Right? Well, sorry, let's just say for clarity. So this whole thing is the actual sample. So we wanted to collect this entire elliptical shaped object. So we wanted the whole thing. With non-response, what ends up happening is that you divide the sample itself into two parts. The part where you have useful information, and that's what actual sample is pointing towards. So this is what we actually got. So just this part here. And then we miss an entire part of the sample, which is this second part here. So where it says intended sample. Okay, so this would have been the missed information. But this would have been what we would have wanted to get. Okay, so again, the idea here, when you have the first one, which was the study error, you have a misalignment between the frame and the target population. The sample error, you have a misalignment essentially between the sample and the target population. Now this could occur because the frame is sitting outside of the target population and then you still use it anyway. So you get a portion of the sample being inside the area that's familiar or similar, and then a portion of the sample that's outside the area that's similar. Or it can occur because of non-response, where let's say this frame was properly covering the target population. So this particular frame sat inside the target population. And then you divide the frame into those that respond and do not respond. Or what I mean is actually the frame gets divided into those who respond and do not respond by nature of non-response. And now the intended sample, so what you actually wanted to collect, this whole elliptical shape, gets split into what you're going to end up with and what you're going to miss because, you know, the people did not respond. So the sample error, again, is a misalignment between the sample itself and the target population. And that can occur because of coverage, or it can occur because of non-response. It's a very difficult problem to control. All right, and then measurement error, which is the last one. This can occur for many different reasons, as I said before. This can occur if there's an interviewer involved because they write something down incorrectly. That can lead to measurement error. It's because people might not give a reliable answer, so they could lie, for example. Or because interviewers change the style or forget the question. All these sort of things can lead to errors. And then the last one I have, measurement error can also occur if the question we pose does not match the question used to define the response variate in the target population. So measurement error can occur if you ask something that's irrelevant, would be another example of one of the ways that this can occur. Again, it's a very difficult problem. Okay, so those are the three major types of error. So again, what we have is misalignment between the frame and the target population, misalignment between the sample and the target population, and then issues with data collection. So those would be the three major error types, or those would be descriptions of the three major error types. Now, as a result of error, in some cases, or just through other reasons, as a result of collection, for example, you can also end up with different biases that you have to take into consideration when you are reporting your result. So there are, again, three major types of bias that we are going to discuss in the course. So selection bias, response bias, and measurement bias. Among the three, response and selection are going to be the most difficult to control. And we're going to later on, we'll actually study mathematically what bias means in terms of the estimation process. Okay, so what is selection bias? Selection bias occurs when non-representative units are included in the sample. So what are some of the ways that this can occur? Well, we saw one of these examples earlier. So this could happen by using a non-representative sample. Okay, so, or a non-random sample. Sorry. Right. So this could just happen if, well, I mean, basically this can happen if you only reach out to a certain, like if you want to collect information about a target population, but you only talk to your friends, or, you know, if I want to collect information about McEwen students, but I only talk to you guys, like this kind of idea can lead to non-representative or non-random samples. So selection bias basically can refer to the collection process in that case. So where did the information come from? Did we, did we institute, if you will, or bring in our own biases because we were, you know, we were running out of time. We didn't properly conduct a random sample because we had to collect the information immediately. This kind of idea. Selection bias can also occur if we specify the target population. Okay. So in this situation, you can imagine that if you want to make a statement about target population A, but when you are creating your frame, let's say you include information from population B and there's no overlap between A and B. Now what's going to end up happening is you're going to be selecting units from population B, which are not representative of or are not to be included in target population A. So this can lead to a selection issue because you're now using, because of your misspecification, you're getting information from a sample from people that should not have been included in the sample in the first place. This can selection bias can also occur if we exclude segments of the target population. Okay, so if we actively don't reach out to certain people that would belong to the target population, of course, this is going to create a bias. And then another example would be substituting elements in sample. So this idea would, for example, let's say you have your frame, you reach out to the people that were randomly selected to your frame, and let's say that the fourth person doesn't respond. So you just ask your roommate for their opinion. So you're substituting your roommate's opinion in for this person that was randomly selected. This could also create selection bias. Okay, so these are different ways that this can occur. But again, the main idea here is just that we are effectively creating, in some sense, a misalignment, or we are introducing or removing elements from the sample, either because we are looking to make it more convenient for ourselves or because we don't want to speak to these particular segments of the population for whatever reason. All of this type of issue can create non-representation and of course can lead to well, what we would call selection bias. Okay, so response bias, this is very similar to measurement error. So this can occur when participants do not give accurate responses to the question. So we already, we've talked about kind of the main ways that this can occur. So we can have an issue with response bias, um, through um, so what was the word I was looking for? So one of the reasons that we can observe this type of bias is participants give misleading answers or no answer. Okay. So that would be the first one. Again, very similar to the idea of measurement error. Now, one of the interesting discussions that we can have about response bias is it can actually be split into two types. Okay. So we can have what is called prestige bias, or we can have what is called recall bias. Okay. So recall bias occurs when the element cannot remember the details to the answer. So recall bias effectively refers to the inability to recall the correct answer. Or misremembers details. And then prestige bias, which is one of the ones that I find kind of interesting, is this refers to the participant bragging or embellishing about their accomplishments in terms of when the answer to the question. Okay. Okay. And then three, this can be due to if the interviewer is present. So if there is an interviewer, response bias can occur for the measurement error style points that we made earlier. So for example, the interviewer writing down the wrong information or misremembering a question. It can also occur if so if recording error committed, or if if the interviewer uses self-selected respondent, for example. So again, I mean, like with the discussion on selection bias or with measurement error, there's a lot of different ways that this can be incorporated or can occur with our results. These are just a few different examples. Again, one of the interesting discussions about response bias is that it can be subdivided into this prestige bias idea, which again I find kind of amusing, and then the recall bias idea, which would be again very similar to measurement error because this inability to recall is likely going to lead to you giving some sort of misleading result, maybe not intentionally. I mean, it's not the case that I'm not trying to imply that every person that comes into the sample is going to necessarily lie on purpose or anything like this, but there are errors that can occur just because, again, you misremember a specific detail, for example. Okay, and then the last issue, so measurement bias. Again, this is going to be very similar to our discussion on measurement error, but this can occur, for example, if if a mechanism for recording responses isn't calibrated. Okay, so what I mean here is if you consider, for example, suppose you're measuring weights, are using a scale to measure weight, but scale isn't zeroed out. Okay, so if you've ever weighed anything before, you can reset the scale before you weigh it. So there's a button on the scale that kind of zeroes it. So it sets it to system zero, if you will, so that when you stand on it, you're going to get a more accurate representation of your weight. Or if you place a food item on it, you're going to get a more accurate representation of how much food you're eating. If you don't zero it out, this is going to bias it in one direction or another. So it's either going to add extra pounds or kilos to whatever you're weighing, or it's going to remove pounds or kilos from whatever it is you're weighing. Okay, so one situation of where measurement bias can occur is if you're using a particular mechanism or machinery that isn't properly calibrated. That's the idea. Another situation could be rounding. So for example, you round all ages to a 5-year interval. Okay, so the rounding error can occur measurement bias can occur based off of rounding. This is kind of a naive or sort of ridiculous example where you're taking age and you're now you're rounding age to a 5-year interval, so you only have 0, 5, 10, 15, for example. But it could also occur if you wanted to give a precise measurement of age and you started rounding to the year. I mean, depending on the situation, this could also create issues because age is something that can be measured very precisely. And then we could also say that this might occur if we sample regions and use incorrect boundaries. Now, I think that this would also have to do with, the idea of study error and misalignment of the frame or of the frame and the target population, but this could also, lead to a type of measurement bias. And again, I think the overall point here is that there is, in the end, there are many different errors that can occur. One of the main things that we're trying to do is avoid using a sample that isn't representative of the population. In most situations, the probability sampling scheme is going to be, or a probability sampling scheme will be the most reliable. And it's also going to lead us to, or give us the ability to conduct inference in a way that is familiar. However, even through those schemes, we're still going to have issues with biases or errors that we need to consider at each of the different stages, whether it be when defining the frame, defining the target population, collecting information. I mean, Error can occur at any of these different stages. And then bias, of course, can be a result of these errors or through some misspecification on the part of the researcher. Okay, so I'll stop there for today. We're almost done with the first lecture set. Again, mainly just an introduction to the idea. So on Tuesday, we'll actually start, or sorry, on Wednesday, we'll actually start looking at some probability sampling schemes, and we'll start to talk about simple random sampling, the estimators associated with that process, how we use those estimators. So we'll start to see some more practical problems and some more familiar inferential style problems. And yeah, so have a good day. I'll post the video after class. I have office hours at 10. And if you have any questions, let me know. Otherwise, I'll talk to you guys on Wednesday.